Every star is born from cold clouds of gas, and every star must eventually die. But stellar death is not a single event. It is a transformation shaped by mass, gravity, nuclear fusion, and time itself. The way a star dies depends entirely on how massive it was at birth. Some stars fade quietly. Others end in explosions so violent they briefly outshine entire galaxies. To understand how stars truly die, we must begin with what keeps them alive. A star lives because of fusion. In its core, hydrogen atoms fuse into helium, releasing enormous energy. That energy pushes outward, balancing the inward pull of gravity. As long as fusion continues, the star remains stable. But fusion is not infinite. Stars are constantly burning their fuel. When hydrogen in the core runs low, gravity begins to gain the upper hand. The core contracts and heats up, allowing new forms of fusion to begin. For stars like our Sun, this marks the beginning of the red giant phase. The outer layers expand dramatically, while the core becomes denser and hotter. Eventually, helium fusion creates carbon and oxygen, but a star like the Sun does not have enough mass to fuse heavier elements beyond that stage. When fusion can no longer continue, the outward pressure drops. Gravity compresses the core, but instead of collapsing into a catastrophic explosion, the outer layers drift away gently, forming a glowing planetary nebula. At the center remains a white dwarf, a dense stellar remnant, roughly the size of Earth, but containing about half the Sun's mass. A white dwarf no longer produces energy through fusion. It slowly cools over billions of years, fading into darkness. This is a quiet stellar death, slow and steady. But for more massive stars, death is far more dramatic. When a star several times the mass of the Sun exhausts its hydrogen, fusion continues in layers, creating heavier and heavier elements. Carbon, neon, oxygen, silicon. Each stage produces less energy and lasts a shorter time. In the final moments, the star builds an iron core. Iron is different. Fusing iron does not release energy. It consumes it. When the core becomes iron, fusion stops providing outward pressure. Gravity wins instantly. The core collapses in a fraction of a second, compressing to extreme densities. The outer layers crash inward, rebound off the collapsed core, and explode outward in a supernova. For a brief period, the star may shine brighter than all the other stars in its galaxy combined. The explosion spreads heavy elements across space. Elements like gold, uranium, and iodine forge in the intense heat of stellar death. What remains depends on mass. If the core is not too massive, it becomes a neutron star, an object so dense that protons and electrons merge into neutrons. If the core is even more massive, gravity continues collapsing inward, forming a black hole. But the death of a massive star is not only destruction, it is creation. The elements scattered by supernovae become part of new stars, planets, and eventually living beings. Every atom of iron in your blood was once forged in a dying star. Stellar death is therefore not an ending. It is a transformation cycle that enriches the universe. The final moments of a massive star unfold with astonishing speed. After millions or billions of years of steady fusion, the collapse of the iron core happens in less than a second. As gravity crushes the core, temperatures soar to billions of degrees. Neutrinos flood outward in enormous numbers, carrying away energy. The rebounding shock wave blasts the outer layers into space. for days or weeks. The supernova shines intensely before fading. The expanding debris forms colorful nebulae that glow for thousands of years. Within these remnants, new stars may eventually form. The universe recycles matter through these violent transitions. Not all stellar deaths require isolation. In binary systems, where two stars orbit each other, death can take a different path. If a white dwarf pulls material from a companion star, it can grow heavier. Once it reaches a critical mass, runaway fusion can ignite, causing a type Ia supernova. Unlike core collapse supernovae, these explosions are remarkably consistent in brightness. Astronomers use them as standard candles to measure cosmic distances and study the expansion of the universe. In this way, stellar death helps us understand dark energy and the fate of the cosmos. Even neutron stars can meet dramatic ends. When two neutron stars spiral together and collide, they produce gravitational waves and a kilonova explosion. These events create some of the heaviest elements in the universe. Stellar death does not occur in isolation. It is part of a vast network of interactions shaping galaxies. Over cosmic time, star formation slows as gas becomes depleted. Billions of years in the future, most stars will have already died. The universe will grow darker. Low-mass red dwarfs, which burn fuel extremely slowly, may outlive all other stars, shining for trillions of years. Eventually, even they will fade. White dwarfs will cool into black dwarfs. Hypothetical objects so cold they emit almost no light, on timescales far beyond human comprehension. Stellar activity will cease entirely. The universe will enter an era dominated by remnants, neutron stars, black holes, and dark stellar corpses. Yet even then, gravity will continue shaping reality. Black holes may slowly evaporate through Hawking radiation over unimaginable periods. The cosmos will transform again. The death of stars is therefore not just an astronomical curiosity. It defines cosmic history. It explains the chemical richness of galaxies, the formation of planets, and the existence of life. Stars are not eternal lights in the sky. They are temporary engines, converting hydrogen into heavier elements and then surrendering to gravity. Some fade gently into white dwarfs. Others explode with blinding force. But every star, no matter how massive or small, ultimately faces the same truth. Fusion cannot last forever. When balance between pressure and gravity fails, transformation begins. And from that transformation, the universe renews itself.